Okay, so I promise a lot less complicated equations in this. So no more complicated equations here. Okay, so what I want to talk about now is preliminary sizing. In other words, you got to start somewhere. Okay. Now, let me preface this by saying that, and I'm going to say this a lot during this presentation, I am not in the next 30 minutes telling you how to fully design a steel plate girder. That's not what I'm doing. But the whole point of what we've been doing in this class, all the Excel, all the complicated sheets that we've been building, is the idea that you take a given set of dimensions and with those dimensions calculate virtually everything else that you need. Okay? But what you're going to find is maybe that girder is not good enough. You know, you calculate all your capacity and you find you've got phi in, you've got mu, there's too much mu so the girder fails, so you've got to change your dimensions. But you've got to start somewhere, okay? So that's what I'm going to talk to you about, okay? And, you know, unless you have an understanding of some of these, you know, approximations and things I'm going to talk about, you know, just coming up with these dimensions, you know, just, oh, it's 14 by 3/4. Oh, it's a 42-inch web depth. It's like, where did you come up with all of that, you know? It's like you're just picking numbers out of the sky, okay? You know, coming up with those numbers without a little bit of a understanding into the background material is pretty tough, you know? You got to have something to go off of. Now, luckily, there's a few resources that are available. One of, I would believe, you know, one of the most valuable resources, and I believe it's probably the most valuable resource, is when you get out of here, you're hopefully going to get a job, you know, and if you're working at a design firm or an owner agency like a DOH or something like that, probably some of the best data that you're going to use to come up with a trial size is where you're at, you know, your firm, your company. If you're at the DOH, the DOH. They're going to have info on historical data on these bridges. You know, if you've got a 50-foot bridge, you know, you're going to have folks there or have data there that's going to help you get a starting size to go off of, okay? But if you don't have that, if you don't have that available to you, and you think, well, how am I going to start? Luckily, there are some approximations, some rules of thumb that you can use to get started, okay? Now, this is also, you know, another resource that I wanted to mention. NSBA is the National Steel Bridge Alliance, and they have a lot of public information available for you. In all honesty, I think the steel industry does a little bit of a better job when it comes to educating engineers and making resources available. You go to the concrete industry, they want money for everything. The steel industry puts everything out there for free, so because they want to sell steels. So I think that they do a little bit of better job at that. They have a lot of span to weight curves that you can find online. So based on a given span length, you can get an idea about how heavy a girder is going to be. But I'm going to break it down even simpler than that and use some rules of thumb. Now, let me be clear, okay? Rules of thumb are approximations. They're shortcuts. They're tricks, okay? This is not the final answer, okay? So that's really important. I'm going to get you a starting size for your girder, but it's not the final answer. Another point about these rules of thumb, a lot of them can't really be derived. You know, you can't set up some big differential equation and solve for x and get these limits. That's not what they are, okay? They're based on experience. They're based off of designing hundreds of bridges, and here's what works, here's what doesn't, okay? Now, a lot of this, just so I'm being diligent and citing my source, I'm getting a lot of this from a fabrication engineer at Hirschfeld Industries. They're a pretty predominant, you know, steel bridge fabricator, and they've published some rules of thumbs that work pretty well. Okay, and again, not the final answer. You'll tweak these a little bit, and that's where Excel comes in. Okay, so what I want to do is start with the girder depth. Okay, so let me start to pass some of this out. So I just realized I hadn't even passed out the notes yet, so let me get these out. So I guess he's coming back at some point. What's that? I haven't passed it out yet. missed something. Okay, so there's that. And there's that. All right, I'll go ahead and give this to you, and you can go ahead and start signing that. Okay, so let's start off with the girder depth, because that's one of the first, I guess, predominant pieces of information that you'll want at the very beginning. Now, what I'm passing out now is a section of the spec that we haven't looked at yet, but there's not a whole lot of, I don't know how to put this politically, there's not a whole lot of super technical information in this section, but there's a lot of just sort of general design stuff, you know, stuff on aesthetics, on live load deflection, on just general info on bridges that's worth looking at. This is section 2 of the spec, and it has sort of a lot of the, hey, here it is on highway bridges. And if you look, one of the tables in section 2, it's table 25263-1. It's traditional minimum depths for a constant depth superstructure. So for instance, if you're looking at a steel superstructure and you're looking at the depth of the I-beam, the depth of the steel beam, if it's a simply supported beam, it's 0.033 times L. So take the span length, multiply it by 0.033, that'll give you how deep the girder is. If it's a continuous span, if you've got a continuous beam, the moments are smaller, so the girder is a little shallower. So that's where 0.027 times L comes into play. Okay? Is everybody kind of seeing where that's coming from? This will also give you an idea if you want to try and determine how thick your deck needs to be, which most cases it's 8 inches. Maybe you need to pop that up to 9 or 10 inches if you've got really, really wide girder spacing. All right. A little bit more basic is to start off with L over D ratios. So traditionally, the L over D, in other words, the length of the segment divided by the depth for a steel superstructure, is somewhere around 25 to 30. Okay, that's one of those experience things. So for us, what the heck? Let's just split the difference. Let's just say 27.5. Okay. So my first equation is that the design depth, the depth of this girder, is going to be the length over 27.5. Make sense? Okay. All right, next one. Let's look at the web thickness. Okay. Now, for a web that is not longitudinally stiffened, we've already looked at this limit. D over TW has to be less than or equal to 150. Okay. Now, you don't want to start getting that high on your web slenderness because you're looking at a somewhat flimsy web when you start hitting the 150s. In a design scenario, you want your web to be a little bit more stocky than that. So let's back that off and let's use 120. Okay. So again, that comes from experience. So a design web thickness would be whatever your depth is divided by 120. So there's a starting value for your web thickness. Okay. Next, let's look at the flange width. Okay. Now, AASHTO requires that BF over D, that ratio has to be less than or equal to 6, or I guess 1 over 6. I guess that's what that should say. But you're talking about a really tiny flange when you start looking at those numbers. Something that's a little more usable is to use a ratio of 4. Okay. So again, comes with experience and it gives us a little bit more of a stocky flange to work with. So let's look at that BF over D ratio as being 1 over 4. So let's use a flange width that's D over 4. Okay? Make sense? All right. Now, this, I did lie to you a little bit ago. This is one of those expressions that we can derive. Okay? Let's look at the flange thickness. Okay? Now, if you go back to all that stuff we looked at a little bit ago, okay, this limit is the limit that determines whether or not a flange is going to locally buckle. Okay? Now, in a design scenario, if we're looking at flange local buckling, usually we don't want that to happen. Okay? Now, on the girder that we just calculated, we did get a flange that experienced local buckling because we were on that linear fit. Ultimately, it didn't govern, though. The LTB of the section did. So what I'm going to do is I'm going to use this, and I'm going to say, all right, let's solve for the flange thickness, because that's what I'm trying to figure out, and this is what I get. The 0.76 comes from 2 times that. Now, the nice thing about this is that I can get a flange limit whether or not I'm dealing with 50 KSI steel or 70 KSI steel. So this is sort of rewriting that limit in terms of flange thickness. So you probably saw a 9.2. Where's the 9.2 coming from? What's 2 times 9.2? What comes out to about 18.4, 18.3 when you round it. So, all right. So a flange thickness for 50 KSI steel, which is more than often than not what you're going to use, would be B over about 18. Okay. For 70 KSI steel, you can back that off a little bit more. Okay. Now, as a rule, tension flanges are usually a tad larger than compression flanges. Typically, they're about 50% larger. So if we assume that the flanges have the same width, why don't I just make the tension flange 50% thicker? And there we go. So let's look at a basic example, and let's see how we could come up with a girder size. Okay? So if I got a bridge that's 150 foot long, so the bridge is 150 feet or 1,800 inches long, and I look at the girder depth, well, a reasonable value to start out with might be L over 27.5. Plug and chug, and that gives me 65.45 inches. Now, in a design scenario, don't use 65.45 inches. Typically, in plate widths, what I like to see is to the nearest inch. That's pretty common. I mean, you might see to the nearest half inch, but usually to the nearest inch is pretty common. So we'll use a web depth of about 66 inches to start out. Okay, to start out. Sound good? Okay. Now, web thickness, okay, D over 120, that's equation 2. So if I take that 66 inches and I divide by 120, I get 0.55. Now, this is where a little bit of more, I guess, background material comes in. I'm rounding this to the nearest 1/8 of an inch, okay? And I'm going to say let's use 5/8. Now, why do you think I'm rounding to the nearest 1/8 of an inch? Well, yeah, but why didn't I round to the nearest 16th? Why didn't I say 9/16? Why did I say the nearest 1/8? It's a common size. All right? That's a good answer, and it's the right answer. Okay? I'm not saying 9/16 plate isn't available. I'm not saying that. What I am saying is 5/8 is probably more commonly available. Okay? We're going to talk about plate availability here in a second. Okay? And again, these are starting dimensions. There's no magic to this. This is just getting you started. All right, flange widths. Okay, now I'm going to assume that the tension flange and the compression flange have the same width, so I'm starting with B sub F. You know, you can say B sub FC, B sub FC, but it's all the same. And I'm saying that's going to be D over 4. You know, backing that D over 6 limit off a little bit. So 66 over 4 is 16.5 inches. I'm going to round that up. What I like to do with flange widths is I like to round them to the nearest 2-inch increments, like 14 inches, 16 inches, 18 inches, 20 inches. That's just typically what I do. So I'm going to round that up and say 18. And you'll notice with a lot of these dimensions, I'm rounding up. I'm not rounding down, okay? Because I find it's a little easier to take a stocky girder that's a little too strong and trim it down. That's sort of just what I find is a little easier. All right, the compression flange thickness, I'm going to assume 50 KSI steel, so I'm going to use equation 4.1. There's my flange thickness over 18.3. Plug that up, plug that in, plug and chug, I get 0.984, so we'll say the top flange is 1 inch thick. And go past that, we say, all right, let's 1.5 times the thickness for the tension flange. I get 1.5 inches for the tension flange. There you go. There's my starting girder. Is that the final answer? No. No, that is not the final answer. That is a starting place, okay? That is a starting set of values, a starting set of dimensions, okay? This is in no way the final size. No way, okay? we're going to need to iterate this. Maybe this top flange is too strong, and maybe we can make it 16 inches. Maybe we can make this 1 1/4 instead of 1 1/2. Maybe we can make this 9/16. Maybe that plate's more commonly available than you would think. I can shave a little bit of weight off that. Okay, does that make sense? This is starting values. Get you somewhere started. Okay, so on your design projects, you're going to have to start with something, okay? You can use this as a guide, okay? But you're going to have to tweak accordingly, okay? Make sense? Any questions? All right. Here's a few more just general ideas. And this is, some of it comes from fabricators, some of it comes from common sense, but this is some stuff I think you're going to want to pay attention to. Okay, number one, if you look at your design project, the cross-section and whatnot's kind of been laid out for you, but in a real-life scenario, even that might not be given to you. Here's the span length go, okay? So if you're laying out the bridge, girder spacing, when you're looking at girder spacing, usually wider girder spacing is better, okay? Now that might be counterintuitive, because you might be thinking to yourself, well, wait a minute. If I make the girder spacing wider, that makes each beam heavier, right? Now, how is that more economical? Well, wider girder spacing means heavier beams, but it also means less of them, okay? Less beams to fabricate means less labor, less time for erection, less cost, okay? It might be a little heavier, but in the end, it's going to be cheaper overall, okay? Make sense? All right. If you have fewer lines of girders, you are going to have fewer cross frames in between those girders. Whole lot less to fabricate. Okay? Rules of thumb. If you've got a span that's less than 140 feet, you want to use pretty wide girder spacing. 10 foot, 11 foot. You want to get it as large as you can. Okay? And that's about your cap off for those shorter spans. Anything larger than that, you want to be going up to like 12 foot, Larger girder spacings, deeper girders, but fewer of them, okay? Now, another point to keep in mind, the wider your girder spacing, the thicker your concrete deck's going to be, because you're going to have more span in between those beams, so you're going to need a larger concrete deck in order to make that happen. In the end, though, that might not be the worst idea, okay? Thicker concrete, maybe more resistant to cracking and whatnot. Maybe make your maintenance department's lives give them less headaches over their life. Yes, sir? You're right. That's another point. The question was about redundancy, and yes, you still want to maintain a minimum of 4 girders. And that's just because, according to our standards and according to our codes, anything less than 4 girders is going to be deemed fracture critical, or at least somewhere on the edge, and nobody's really going to use it anyways. But what I'm getting at is if you've got a really wide structure, if you're talking about a 4-lane bridge or something like that, use as wide a girder spacing as possible. If you can eliminate a girder line feasibly, do it, That's a good question, and that's a topic of debate. Some people do and some people don't. People know that people think 2 girders. Well, 2 girders are fracture critical. 4 girders aren't. Well, where's 3? Yeah, I've asked that question to different bridge engineers. I get a different answer every time. And then as soon as people start talking about it, they say, well, I'm just going to use 4 girders, and then I don't have to worry about it. So personally, I think you could get away with 3 girder bridges, especially on creek crossings and short bridges and things like that. I don't think it's that big of a deal, but, that's me. So that's what I would do. But I wouldn't use a 3 girder bridge on like an interstate overpass or anything like that. But on some low volume creek crossing, I don't think it's that big of a deal. But that's me. This is an image that I wanted to show you all because I think it's hilarious to kind of illustrate my point a little bit. I know it's a little blurry, but this really sort of hones in what I'm talking about. This is a series, this is a construction project going on, I believe this was in Pennsylvania. And what you're looking at is the pier region for these two bridges that were reconstructed side by side. The idea was the traffic got a little heavier, so they needed to up the superstructure capacity in order to meet the demand. And if you look, it's the same bridge, the same spans. This one has 4 beams, this one has 6. I don't get it, you know. 6 beams, that's another set of beams that need to be fabricated. Think how many cross frames that need to be fabricated and bolted together in the field. That's just way more expensive. Why would you do that? Oh, you say, oh, the girders are 5% lighter. You know, in the end, you just up the price of that project substantially, right? A steel fabricator there, he knows what I'm talking about. So, make sense? All right. Okay. Some other key ideas, plate thicknesses. Here's some minimums to go off of. Stiffeners and connection plates don't go lower than 7/16 of an inch, and 1/2 of an inch is preferred. 1/2 inch, you're going to find 1/2 inch plate all day, every day, okay? You know, you think about commonly available plate thicknesses and plate widths, and you could probably use your gut, and you're probably going to be right. I mean, think about it like this. What do you think's more commonly available, I guess I should say? 1/2 inch plate or 19/64 plate? 1/2 inch plate, right? It's a common dimension, right? Common dimensions you're going to find more common, you know? So, you know, you got to think about this, you know, a little bit logically. You know, if you're the design engineer, are you going to spec out a 19/64 plate that's going to have a lead time of 6 months, you know? Why don't you just spec out the 1/2 inch plate or what have you, and you'll get it in 4, you know? Make sense? So, you know, make sure you're using a little bit of common sense on your dimensions. Webs, because webs take up a lot of steel, I guess a fair point would be usually your webs are selected in 1/16 of an inch increment, because you've got a web, but it's really deep. So that is a lot of steel, so maybe you want to look at 1/16 inch increments. Flanges are usually in 1/8 inch increments up to about 2.5 inches. Anything over that, you're going in 1/4 inch increments. Usually the minimum size flange that you'll see is 3/4. You usually won't see anything lower than that. You start seeing stuff lower than that, and you start getting issues with slender flanges and local buckling, and it becomes it's undesirable. Plus, a lot of this stuff has to do with handling. You know, if you try and fabricate a girder with like a 1/4 inch web or something, you might have all the capacity demand that you need, but your fabricator is going to be yelling at you because, you know, if you ever handle structural plate, you know, by itself, you know, try and lifting it, it's got all the stiffness of a piece of wet spaghetti. You know, it's pretty floppy, you know, and you've got to take this and weld it to other sections, and it's got to maintain its shape. It gets tough to handle if you use really, really thin sections, even if the math works out and the capacity's there. So there's a little bit more to it than just the math. You got to think, you know, with a little bit of common sense, okay, in terms of the sizing. Everybody okay with that? Okay. All right. You also have to look at plate availability in terms of what's available and what are the maximum lengths available. For instance, you know, if I'm looking at a plate that comes in standard widths, I think I've mentioned this to you before, that structural plate comes in standard widths. You know, when you go to Lowe's and you buy lumber, it comes in standard sizes, 2x4s, 2x6s, 2x12s. Well, plate comes in standard sizes as well. Typically, it'll come in standard widths, like 72 inches, 84 inches, 96 inches. And some people might want to take those and fabricate press brake form tub girders out of them. You know, a little bit of shameless self-promotion. Going back to this, let's say I'm designing a girder and I'm using 1/2 inch plate that's 96 inches wide. Well, that field piece, the maximum length that I'm going to feasibly be able to find is 972 inches. Okay? The point I'm making is if I have a bridge that's longer than 972 inches, what I'm going to have to do is CJP those together. I'm going to have to weld those plates together. So you need to think about commonly available plate widths. You know, If I'm using this thicker plate for the same span, I'm going to have to use more of them, a lot more CJP welds, a lot more time, a lot more cost. You got to think and use your noggin a little bit. What is the most optimum selection? Everybody okay with this? Okay. Don't spec out a plate that's not standard, okay? You start asking mills or service centers to produce plates that aren't of standard size, they're going to bump the cost up and they're going to bump the time up. So don't do that, okay? Everybody all right with that? All right. Now, this is one I'm going to do a little bit of artistic drawing on here in a second, but when you're sizing flanges, it's very common to reduce the flange size a little bit. For instance, if I've got a beam that's, let's just use some basics. If I got a beam that's simply supported, let's just go to basics, and it's subjected to a uniformly distributed load, right? Would you agree that the moment diagram looks something about like that? Everybody okay with that? So my point being, you do not need the absolute maximum size of that girder everywhere. You really only need it right here, okay? Which is why if you look at girders and longer span bridges, what you find is this. Here's your flange. There's that. There's your flange. And then somewhere in the middle, that flange gets larger. That flange gets larger. Make sense? We have a flange transition. There's a point when you're going down and then the flange suddenly gets thicker, right? You don't need that massive flange right here where there's hardly any bending stress at all. You need it out at midspan, okay? So if you look at your flanges from abutment to abutment, you might use a really thinner piece and then it gets really thicker, okay? Make sense? Now, my point being, I'm going into this a little bit, my point being, never, ever, ever, ever make the flange wider, okay? If you're going to do a flange transition, only make the flange thicker. Never make it wider. I'm going to explain why, okay? All right, let me show you a little, let me learn you a little bit about the fabrication process, okay? Let me show you how this is going to work. Okay. Let's look at option 1. Okay, and this is changing flange thickness. Okay, so here's how this is going to work. Let's say you got to cut 4 flanges out of some plate. Okay, so you got 4 girders and you got to cut 4 flanges. And you've decided to make the flange thicker. Well, here's what you're going to do. You're going to go to the mills or the service centers and you're going to buy that 96-inch wide plate, 84-inch wide plate, what have you. Here's what's going to happen. You're going to take a big 84-inch wide plate or 96-inch wide plate and you're going to set it down like this. Okay? So here's this. You're going to buy another 84-inch wide plate that's a lot thicker. Then you're going to have your thinner plate here. So something like that. Sound good? Okay, so that everybody's clear on the dimension, this is 84 inches. Okay? So let's say when this is all said and done, you're going to have a bridge that's, I don't know, 120 feet long. What have you. Okay? So this is we'll make up some numbers. This is, 3/4. This is 1 inch, and this is 3/4. Are we okay with that? Okay. Now here's what they're going to do on the fabrication process. Okay. First thing they're going to do is they're going to do a beveling operation right here. And the beveling operation is, if I have a thinner plate being welded to a thicker plate, the idea is to bevel some of this off so that, you know, when it's all said and done, it looks like this, so that I can start filling it with weld and welding those together. Something about like that, right? So we're going to bevel these ends, right? Then, next thing I'm going to do is I'm going to weld what are called some runoff tabs. We'll weld a tab right here, weld a tab right here, weld a tab right here, and weld a tab right here. And the idea behind that is this. So let's say I've got plate 1 and I got plate 2, and I'm going to weld them together. I'm going to weld a little bit of steel right here and a little bit of steel right here so that when I'm welding, I can run off a little bit. You know, we're not talking about, 2 feet. We're just talking about, a little bit of plate right there. Sound good? So then I'm going to, weld. All right, sound good? Then I'm going to get my acetylene torch out. And I'm going to cut out my flanges. So, maybe cut down the middle. Maybe cut like that. Maybe cut like that. Cut like that. Cut like that, or what have you, right? So I have these big strips, and they're going to be my flanges. Everybody okay with that? Then I grind off my runoff tabs, and my flanges are done. Simple, right? Now, here's what happens if you change the width, okay? So what happens if you change the width is this, okay? You start out with a plate like this, but the center, if you're changing the width instead of the thickness, that means it's got to get wider, right? So that means you got to start out with a much wider plate. Maybe this is 84 inches, and now you're dealing with a 96 inch, right? Sound good? All right, and then you're going to have another 84. So now what you've got to do is right off the bat, you've got to cut, okay? So you got to start off by doing this. And the same thing here. The same thing here. Same thing here. Same thing here. Okay? Then, for each one of those little strips, now you've got how many different strips flying around all over the place? You got 12 different plate strips that you got to manage. That's going to take up space in your fabrication shop. And taking up space in the fabrication shop takes up time and takes up money, okay? That's going to increase the cost. Now, for each one of these little strips, you're going to have to, you're going to have a strip here. You're going to have a strip here. And you're going to have a strip here. Then you're going to have to, bevel. It's usually pretty common to cut that off kind of like that, cut that square edge off a little bit so it kind of looks like that. You're going to have to do that. You're going to have to weld you some runoff tabs. Weld you some runoff tabs. You're going to have to weld. Then you're going to have to grind off those runoff tabs. Then you're going to have to take this, pick it up, put it somewhere, and then do all that again. And then do it all again. Then do it all again. The number of flanges that you have. Instead of doing it all at once, now you got to do it how many different times? It's going to bump up the fabrication costs, right? That's point one. There's another big reason why you don't want to change the flange width, especially the top flange width. Because as soon as you change the top flange width, it's going to make your form work a lot harder to deal with. All right? You can have the same constant flange width on the top. It's going to make putting your form work together a lot easier. That make sense? All right. I had a question earlier about cross frame spacing. How far apart do you want to space your cross frames? A better way of looking at it would be, instead of looking at how far apart to space your cross frames, the best way to look at it is, how can I eliminate as many cross frames as possible? I would say on average, cross frame spacings tend to go around 20 to 30 feet. There used to be this rule in the spec that your cross frame spacing couldn't go above 25. It's not in there anymore, but it's funny how everybody kind of still uses that. And cross frame spacings don't really tend to get that much larger than that anyways. But what I would say is if you've got a span arrangement and you can get away with using, let's say, 6 cross frames as opposed to 7, and it's not going to appreciably change your LB, I would do it. Because that's a fewer set of angles and channels that need to be fabricated, fewer set of holes that need to be drilled, fewer set of stuff that needs to be put together in the field. Make sense? Okay. Another point I should mention, if you're laying out, maybe I should do this. If you're laying out a cross section, so here's your concrete deck, right? And you've got a beam here, beam here, beam here, beam here. Okay, so this dimension is your girder spacing, and that's your overhang, right? On average, what's economical is about 30% of your girder spacing for that dimension. So if you've got a 10-foot girder spacing, use about a 3-foot overhang. That's pretty reasonable and pretty economical. I've heard, numbers that say go from 28% to like 35%. 30. That's easy to remember, and I don't think it appreciably changes things anyways. I mean, 28% versus 30%, I don't think that appreciably changes anything. Yes. Oh no, no. That's no, yeah. It'll go up because what they're going to do is that's going to go flush with the web. Yeah, no, that's a good question. That's going to go flush with the web. They're going to fill this in, and then when it's all said and done, what they'll do is this. You'll have, plate 1, and then you'll have, plate 2 that's been flushed like that. What they'll do is they'll then grind that smooth. And it's usually, comes out something like that. I think that's usually like it's like a 1 to 2.5, something like that. So that you have sort of a seamless transition. But we're talking like that, something like that. Yeah, but that's usually what they'll do. The big thing is to not do that, 8 times. Just do it once. Yes, sir. What do you mean? What calculate? Well, it's the same thing with positive bending region and negative bending region. Your flange size changes, you just have different section properties. Are you talking about right there? What section properties do you use for your stresses? Like right there? Oh, okay. Well, the easiest answer is that's why we use 10th points. We don't just use the moment at midspan. We calculate moments at various different points along the span. So I can look at that particular point and say, I can take, right about here, I can probably bump that flange thickness down a little bit. Now, a good rule of thumb that I've heard and kind of went with is I don't usually include a flange transition unless it's going to save about 1,000 pounds of steel, overall on the girder. I mean, it is more headache. So if you're going to do it, there's got to be a good reason to do it. And the number I've heard is if it's going to save about 1,000 pounds of steel on the girder, do it. So, and that may seem like a lot. It actually really isn't. So, when you start adding it up, I mean, a little bit of thickness over 40 feet on both ends, that adds up. But that's where we use the 10th points. We've been focusing on 0.5L. Well, if you're going to do a flange transition, you better focus on that 0.2L. Because for that end segment, that's where the maximum moment is for it. Does that make sense? That's a good question. That's a really good question. And the answer is using that. If you were really trying to get, down to the nitty-gritty, you could use 20th point moments. You know what I mean? Get more accurate moment data. I mean, there's a point when close enough for government work, but, Yes. Because you would need to determine, well, what's the capacity right there? You see what I mean? You're right, and the answer is yes. It's a little bit better than all those equations, right? A little bit better? All right. Let's go ahead and call it this time, because next time what I want to do is this, okay? Right now, you all should have the tools at your disposal to do all the calculations for service and strength limit state in bending for your design project, okay? Now, we haven't done deck casting yet. We'll do that later. I want you to have a little bit of experience with this math and these equations so that you can come prepared to discuss constructability. But next time what I want to do is talk about shear. Shear is its own nifty, unique animal. Everybody good? All right. Don't forget, y'all have a homework due next week, and that's all I got for you all. We'll see you next week. Y'all have a good week. Oh, that's a good question. So, yeah, I guess we are going to have class next week. I'll pause the recording at times. Maybe we'll pull up the electoral map and see if the purge is going to start early or something. That was a joke, not a very funny one. But we'll pull it up. We'll pull up and see if, Clinton or Trump is going to, be running the show for the next 4 years or what have you. So, yeah. We'll make it an entertaining lecture in bridge engineering. How's that? But if you feel like you've got to miss because you want to stay home and prepare for whatever apocalypse you think's coming, I'm kidding. I guess I'll be nice and excuse it, but we press on in here, so you can make your decisions there. Again, I record everything, so pay attention to your Blackboard and MU Online and your recordings, but I'll leave it at that. Sound good? All right. We'll see you maybe next time. So, all right. We'll see you.